he really realized that I was really going through a very bad time, because he immediately took very good care of me. He was especially warm with me in these very first moments in Syracuse, and actually he helped me a lot settling and organizing my life in Syracuse. Eventually, my wife and my daughter joined me a month and a half later, and both families, we became friends, and I enjoyed very much his company for the year that he was in Syracuse until he moved to Gainesville, I think. So I even have some sports anecdotes, in particular a very crazy tennis match that I played with him, but I don't have much time, so I will talk about that in some other occasion. What I want to say is that it's really a honor and a privilege to be here celebrating an extraordinary scientist, a wonderful person, and a very dear friend. Okay, so let me start with my talk. Now, the motivation is the following. If you look at the title of the workshop, you will see that there are several subjects that Jurek has worked on. In particular, he has worked on canonical methods, quantization methods for general relativity. He has also worked with isolated horizon, that means space-time boundaries. So I will be giving a very simple talk about how you deal with Hamiltonian formulation of field theories with boundaries. This seems a rather simple thing because, as I say here, in principle, there are no obstructions to formulate, to get a Hamiltonian formulation for theories with boundaries. But then in practice, when you look at examples, sometimes you see that life is not so simple. So what I will do here is go back to the Dirac method, show you how it can be reformulated in geometric terms. And I'm not referring here to the interpretation, the standard interpretation of constrained submanifolds as first class or second class, but rather to really the geometric interpretations, that the steps that you follow in Dirac's algorithm to get your formulation in phase space. And I will show you how, in practical terms, if you follow this geometric version of Dirac's procedure, you will find that it is very convenient, very easy, and you can avoid, in practice, computing Poisson brackets in the presence of boundaries, which may be tricky, okay? This is one of these words, exegesis, that I use in the title that I have to look up in the dictionary every time I find it. This happens also with hermeneutics, so I write the meaning here. So it's a critical interpretation of a text, in particular, a sacred text. And in fact, one of the sacred texts that I have in mind is this very thin book where Dirac spelled in very concise terms what his algorithm is, and the one that we use and follow all the time. Of course, I'm oversimplifying here because many other people started looking at the Hamiltonian formulation of constraint systems, in particular Peter Bergman, Anderson, Rosenfeld in the 30s started studying the Hamiltonian formulation, and we even have people here who witnessed these developments in Syracuse, Ted Newman, Josh Goldberg. So I will really concentrate on this, okay? So let's move on. Now, very quickly, the Dirac algorithm. I will review it very quickly for you because you all know this stuff. So the idea is that sometimes when you try to find the Hamiltonian for a system and you try to get the momenta in terms of positions and velocities, you realize that you cannot always solve for all the velocities in terms of positions and momenta, and this means that there are constraints. This is what Dirac calls primary constraints. Now, while you detect these things, you try to build a Hamiltonian, but there are some problems with that. So what Dirac tells us to do is, well, to build a total Hamiltonian in which you add some funny multipliers, whose meaning is not completely clear, at least when you read Dirac, and you add the primary constraints, okay? Now, you have to enforce the consistency of these constraints in time under the evolution defined by this total Hamiltonian. So you have to compute something like this, a Poisson brackets of the constraints, and enforce that these things are zero, at least when you restrict to the primary constraint some manifold. Now, there are several possibilities. It may be that your theory is inconsistent, so there is no way to satisfy those conditions. It may be that the conditions are trivial, then of course you are done. It may happen that these Dirac multipliers don't appear in the consistency conditions, and when that happens, you have additional constraints that are called secondary constraints. And then it may be that you can solve these consistency conditions for the Lagrange for these Dirac multipliers. If you can do that, you finish. Okay? So generically, you will find these secondary constraints, and of course, consistency of dynamics forces you to consider the stability under the time evolution. Okay? Here, the stability under the time evolution is the evolution defined by the total Hamiltonian. So you don't have to build a more total Hamiltonian, but just stick to what you had at the beginning, to this total Hamiltonian. Well, if you look at the equations, these equations are actually, they may be complicated. As you can see, these are linear for the Lagrange multipliers. That's fine. But these are inhomogeneous. So sometimes you may have conditions, additional conditions required for these to have solutions. Sometimes the rank of this matrix here, which depends generically on the position variables and the momenta, may change from point in phase space to some other point of phase space, so you have bifurcation, and that's a problem. So there may be difficulties, but at the end of the day, as I said before, you can usually solve for these equations in terms of the Lagrange multipliers. Generically, you will have some fixed part in the solution, some arbitrary parameters in the solution, and with those, you can build a final Hamiltonian that defines consistent dynamics, which is equivalent to the one given by the singular Lagrangian that you started with, okay? And you find a bunch of constraints, and the meaning of these constraints is that they tell you what are the allowed initial data that you can use to solve this, for your problem, okay? And will give you the dynamics. Now, some comments on the Dirac algorithm. Well, if you read the book, at least when I did that, there are some parts that are slightly difficult to understand. So for example, there are statements such as these, the Poisson bracket. This Poisson bracket is not defined, but it is multiplied by something that vanishes. So the first term of some equation vanishes, things like that. So there are some things that sound strange. Also, Dirac says very clearly that there are no difficulties when you move to field theories where you have an infinite number of degrees of freedom. That's probably not always the case. But a very important message that I want to convey is that this notwithstanding, you follow the algorithm to the letter, it works perfectly. And if you interpret the results, everything works just fine, okay, as it should. So let me show you an example, a very simple example of a field theory with boundaries, probably the simplest one that you can come up with. This is a scalar field defined in a segment, the interval 0, 1, and you want to enforce Dirichlet boundary conditions. Of course, you can do that from the start by working in a configuration space consisting of functions satisfying the Dirichlet boundary conditions. You can do that consistently, okay? But let us suppose that you want to enforce those conditions dynamically, that you want to add some other additional variables to your Lagrangian in such a way that these conditions are dynamically generated when you look at the stationary points of this action, okay? So in order to do that, I add two additional configuration variables, which will be actually Lagrange multipliers, that enforce these conditions. Phi at 0 is some concrete value that I call phi 0, and phi at 1 is some concrete value that I call phi 1, okay? And I will, during this talk, I will not care too much about analytic issues. I will suppose that things are smooth enough for everything to work, but I must stress that at some point, you must really be very careful with functional analytic issues if you want to formulate your field theory correctly, okay? So just keep that in mind. So you write this. Of course, you expect that the dynamics is what you want. In any case, it's always a good thing to check if you get the right field equations. You compute the variations, complete the standard thing, And you get this bunch of conditions. First one is just the wave equation on the interval, perfect. I get, as I expected, the boundary conditions here. And then I get two extra conditions that are only telling me what the values of these Lagrange multipliers are. So I'm in good shape. So even though, strictly speaking, I have enlarged my configuration space to have some additional variables to enforce the Dirichlet boundary conditions, the solution, when I look at the field equations and their solutions, they're in one-to-one correspondence with the ones coming for a scalar field with Dirichlet boundary conditions. Very good. So let's try now to apply Dirac's method to this action and see what happens, see what we get. Well, you start by computing the momenta. You start with that. Of course, the momenta canonically conjugate to the field are just the velocities. And then, because these Lagrange multipliers appear, they don't have time derivatives in the action, you will get that their momenta are 0. So these are primary constraints in Dirac's parlance. So we get two primary constraints. The P0 is equal to 0, P1 is equal to 0. Now you have the canonical Poisson brackets. These are the non-zero ones. This is the total Hamiltonian. You have a piece, which is given by an integral. You have two extra terms that come from the Lagrange multipliers. And then you add the primary constraints with two Lagrange multipliers, or Dirac multipliers, u0 and u1, okay? And now what you have to do is to enforce the stability, the dynamical stability of these primary constraints, okay? And as we will see immediately, when you try to do that, there is a question that you have to answer yourself, which is not an academic question, it's actually relevant. I will show you that it really plays a role, which is the following. So for example, what is the value of this? If I evaluate the field at 0, the momentum at 0, what do I get? Do I get 1? Do I get delta 0, 0? Is this relevant? So just to answer to that question, let's follow Dirac's method and try to see what we get when we force the stability of the constraints.
So to follow the Dirac's method, however, since you are imposing the Dirichlet boundary conditions as constraints, therefore the phase space can define pi with no restrictions.
Yes. Yes, precisely that. Yes. So when you compare the Poisson bracket of the total Hamiltonian with P0, you get this, which is perfect. This is the Dirichlet boundary condition that we expect to find. Good. So far, so good. Let's now enforce the stability of these. You do the computation. Well, here you have something slightly uglier, because at some point you have to compute this Poisson bracket, which is a delta sitting in one of the boundary points. So there are prescriptions to deal with these things. For example, you can, instead of saying that this is a delta, you can put a 1/2 in front of it. There are some things that you can do. They may be a little bit ad hoc, but here still they give you something. So you get this extra condition that the momentum canonically conjugate at 0 is 0. So okay, even though you had to fiddle around a little bit with this Poisson bracket, it seems to work. But then when you go ahead and you impose the stability of this thing, then you're really in trouble, because somehow in the expression that you get, there is this, on one hand, you will find a thing like this, Poisson bracket of phi 0 at pi 0, but then you will have this thing inside an integral, so you will have to, somehow in one part, you will have to use this as if it was a 1. On the other part, you would need to fix this as if it was a delta. So it's actually messy. What happens in practice, if you know the final result, and if you can find papers, actually highly quoted ones, where people find ad hoc procedures to follow with the algorithm, but at least my particular impression is that in those cases, people really know what the answer that they want to find, so things are somehow set up to get to the right answer. When I get here, I don't know how to continue, so this tells me that it may be better to have a different perspective to avoid this kind of difficulties. So this is what I will discuss now.
But isn't that a problem even if pi equal to 1/2, pi equal to 1/2? Is that equal to 1 or 0? Equal to 1 or delta of 1?
No, what I mean is that if I put a 1/2, then I would get 1/2 of pi 0. So here,
We don't know what it is, right?
well, we don't know what it is. Sure. So the difficulty appears here, okay? So even if you try to push ahead here, which is relatively simple, then the next step you are done, okay? And you don't know how to continue. So the way out of this is to take a different approach to this and look at the algorithm from a geometric perspective. This is something that mathematicians have looked at since the 70s, so people really understand, at least from a theoretical perspective, what you have to do, even though in practice they don't compute so many examples. So when you have to, they don't work out so many concrete problems, okay? So the idea is that you take a more geometric perspective. This is just a picture to just convey the idea that while you have Lagrangian formulation, something that you have in the tangent bundle of the configuration space, which is where you write your Lagrangian, you have to go to the Hamiltonian formulation, which is formulated in the phase space, which is the cotangent bundle of the configuration space, and you pass from one side to the other by using the definition of momenta, which is called by the fiber derivative by mathematicians. So let me say some preliminary things about this geometric perspective on the algorithm, and then let me tell you how you rephrase the computations that I showed before in these geometric terms. So the goal, again, is to find a Hamiltonian defining the whole phase space. This is very important from, if you really want to implement the quantization program a la Dirac. There is a well-known approach, which is called the Gautain-Nestor-Hintz approach, that is done only on the primary constraint hypersurface. So from the point of view of getting Hamiltonian vector fields at the dynamics, it's enough. But of course, if you are thinking about quantization, it is different. So it's really useful to really stick to the Dirac method, okay? So the dynamics takes place on the primary constraint submanifold, which in more abstract terms can be thought of as the image of the tangent bundle of the configuration space under this fiber derivative, okay? And what you're looking for when you want to describe the dynamic is a Hamiltonian vector field that, restricted to this submanifold, where the dynamics takes place, must be tangent. So this idea, this apparently trivial idea of tangency of the Hamiltonian vector field to the constraints submanifold that you have to find in phase space is really the gist of Dirac's algorithm. Once you realize that you have this tangency condition, there are some things that get very clear, and even from the computational point of view, as I will show you, are very useful. So the starting point is actually, the steps are the same as in Dirac algorithms. So the starting point will be computing the momenta, we'll be getting this fiber derivative. Regular systems are those for which this fiber derivative is a Diffeo, so it's invertible, everything is nice. Singular systems, constraint systems, are those for which this thing is not a diffeomorphism. Actually, there are many possibilities. So for example, this map may be injective, but not onto. In that case, usually you have a submanifold, the image of the map is a submanifold of phase space, which is a primary constraint submanifold, but you can have more complicated situations, more pathological ones in which even this type of approach may not work. But let's suppose that we are in a nice situation in which this primary constraint is submanifold is actually a submanifold, and it is given by some functions of momenta and positions, as in Dirac's method. Now, there are theorems that tell you that what you have to do in this case is to solve this type of equation, where you have a vector field, Hamiltonian vector field, that you have to determine. You have the symplectic form. Let us suppose that it is strongly non-degenerate, so that everything is nice, invertible, and so on. This is the Hamiltonian. These are some multipliers, which are not specified, and these are the differentials in phase space. All these things live in phase space of the primary constraints that must be always preserved in time, okay? So this is the type of equation that you have to solve for these guys here, for these vector fields. But there is a very important condition, consistency condition, that you have to enforce, as I mentioned before, which is that this Hamiltonian vector field must be tangent to the primary constraint submanifold. So the directional derivatives that I am writing in this way to emphasize the fact that you don't need to compute Poisson brackets in order to compute them, to get them, must be such that this is 0 when you restrict yourself to the primary constraint submanifold, okay? So again, it's very important to see these things as directional derivatives and to realize that you don't need Poisson brackets to compute them. Now, several things might happen at this point. So for example, this tangency condition may be identically satisfied. If that happens, you are basically okay, and that's it. But it may happen that the tangency condition is actually satisfied only on a proper submanifold of the primary constraint submanifold. So in that case, you will get additional constraints. These are the secondary constraints. And you will have to require that the Hamiltonian vector field, that you must realize that you find in this first step once and for all, even though there may be some parts of it that are not determined, that vector field must be tangent also to these secondary constraints. And as it happens with the standard Dirac algorithm, it is also possible that the tangency condition fixes some of these arbitrary multipliers, okay? So, as I said, in the first case, and bam. In the second case, I have to keep on requiring tangency. And in the third case, I will find some multipliers. At that point, my algorithm will stop. And it's a theorem that the dynamics that you obtain by projecting the integral curves of the Hamiltonian vector fields onto the configuration space is the same as the Lagrangian dynamics. And by following this procedure, we also obtain the initial conditions that the initial data must satisfy in order to have consistent dynamics. So let's go back to my example and show you what you get when you follow this procedure. I'll show you actually it's a convenient way to do the computations and interpret the solution. So I will just concentrate to the homogeneous case. There are no basic differences. So just to lighten a little bit the slides, I just put phi of 0 equal to phi of 1 equal to 0. I will take this Lagrangian. This term here has a spatial derivative, so this is exactly the one that I wrote before with the two Lagrange multipliers. It's only that for convenience, this is completely equivalent to the other thing. For convenience, I just add an additional field, which I call psi. I compute the momenta. The momenta are dual objects, so if you are in the fibers, they are covectors, and they are like this. One of them, you get something which depends on the velocity, so here you have no problem. But you get this other condition, which is that the momenta canonically conjugate to this psi field, which is the one that I use to enforce the Dirichlet boundary conditions, is 0. So this is a primary constraint, okay? I can write the Hamiltonian, which is defined in principle uniquely only on the primary constraint submanifold, but I can extend it easily to the full phase space. This is actually one of those extensions, but there are more if you want. Now, vector fields, how they do like? Well, vector fields, vectors, for example, tangent to the cotangent bundle, sit on points which have configuration variables and momenta, and in fact, and it can be written like this. So these are the components of these vector fields. Of these components, two of them are just functions. The other two are dual objects, so they are covectors. Let's suppose, and it is consistent to do this here, although that is one of these functional analytic issues that at some point you will have to take into account, that these covectors can be written like this, acting over functions, like integrals, okay? Now, I have to solve this equation here, so I have to compute several things. I have to compute the differential of h, this term, and this term over here with the symplectic form. Now, the differential can be written immediately. I have an integral here. I'm writing the differential acting on an arbitrary vector field in phase space. So I have this term, and I have a couple of boundary terms. The canonical symplectic form acting on pairs of vector fields is like this, has a simple expression. I need also to compute the extra term with a constraint. It will be something like this. And then I have to solve this equation, the one that I showed before, for every value of this extra field that I call y, okay? Now, when you write things in this way, this can be done very easily, because if your symplectic form is strongly non-degenerate, you know that the previous equation will have unique solutions. So if you find the solution, you know that that is all, okay? And when you set up the computations like this, actually you can solve the equation just by comparing by both terms. For example, I have this arbitrary field here, y pi phi. It appears here only here. So immediately this tells you that this component of the Hamiltonian vector field will be equal to pi phi. Same thing happens, for example, with this one. It will give you this component in terms of the second derivative of phi. And for some of the components here, one of them will be 0, and the other one actually will involve these Lagrange multipliers. So in one stroke, you see that you can get these x, these components of the Hamiltonian vector field, immediately. And you didn't have even, at this stage, you didn't have to compute Poisson brackets. You have also some extra conditions because you have these boundary terms, and you can justify easily that these things have to be separately 0. But as I said before, if you know that your problem has a unique solution, once you can actually check that when you take these components for the Hamiltonian vector fields and the extra conditions coming from the vanishing of these and these, you will get these and these conditions here, okay? So it was very simple. You didn't have to invert the symplectic form, but just to match terms into expressions. And if you are in a good situation, for example, when the symplectic form can be inverted, then you know that you have the right solution. Now, what are these things here? So let's see. I have not fixed completely this Hamiltonian vector field. There is an arbitrary element here, which is this multiplier. I have these constraints, and these are things that I expected. I have the Dirichlet boundary conditions to begin with, and I have these extra conditions fixing the values of the Lagrange multipliers at the boundary, which are exactly the ones that I got when I wrote the equations of motion. So this is okay. And now what I have to do is enforce the stability of these things, okay? And in order to do that, I only have to compute directional derivatives. So when you do the computation, you get these three things. And the first one gives nothing new because this component of the Hamiltonian vector field was 0 to begin with, so perfect. Here I get actually a couple of conditions, one at 0, one at 1, that are fixing the value of this field at the boundary, okay, to be the value of the moment at 0, the moment at 1. And this other tangency condition gives me this other extra condition, which is actually fixing the value of the Lagrange multiplier just at the boundary, at 0 and at 1. So this is what I get at this stage. I have to continue because I have some extra secondary constraints, which are the vanishing of the momenta at the boundary. So then I press ahead. I have to compute some extra directional derivatives. And for example, the first, I get additional conditions. The first one that I get is this one, that the second partial derivative of phi must be 0, both at 0 and at 1. And if I follow, that I actually get an infinite tower of constraints of this type, telling me that the even derivative of both the field and the momenta at 0 and at 1 must be 0. Now, this tower of constraints, this is not the new result. Mathematicians know that if you want to solve this problem, these appear as consistency conditions. But it is very nice to find them just by following Dirac's algorithm in these geometric terms, because these are not that trivial to find. In particular, if you try to press ahead with the initial computation using Poisson brackets, it's a mess. And again, there are papers that you can look up in the literature where people pretend to do this, but at least to me, the prescriptions that they use are very ad hoc. Where here, I'm just sticking to a very clear geometric procedure, enforcing tangency. Actually, it's nice to try to understand what these conditions mean, because the ones that appear previously are quite clear. One, you have the Dirichlet boundary conditions. Of course, you have to have those. You have some other conditions fixing the Lagrange multipliers. That's OK. But what do these things mean? So let me finish by giving you the interpretation of those, of these constraints. So, well, this summary of what I get. So what you see is that you get a Hamiltonian vector field, you have this primary constraint, you have this whole bunch of constraints, and then Lagrange multiplier is arbitrary in the middle of this interval, but is forced to be 0 at the boundary. And by continuity, this means that any function that vanishes here and here is good as this Lagrange multiplier. And this is essentially telling me that the value of this field, extra field that I added to enforce the Dirichlet boundary conditions is just fixed at the boundary and it's arbitrary in the bulk. Okay? So let me just tell you the interpretation of these constraints, new constraints, and I will finish. Now, suppose that you want to build a concrete solution to the wave equation in the interval 0, 1 for some initial data which are like this, and you have 0 velocity. So let's just consider a simplified situation in which the value of the time derivative of your field at the initial moment is 0, okay? Now you can use, for this purpose, you can use the D'Alembert formula. So basically you divide this thing by 2, you extend it in an odd way, both to the right and to the left, and then you can build your solution by just adding left movers and right movers. So when you do that, you see that, for example, now the pink curve and the blue curve are just a right mover and left mover. This is a displacement. This is just a smaller step after the initial moment. Then what you see is that you will always have enforced a boundary condition, because as you are using a dot extension, when you add up these things at the boundary, you will always get 0. But then there is something important. Let's move forward a little bit more. And this is the following thing. If you want your solution to be C-infinity, to be smooth, you really need that these odd extensions that you use to build your initial data must be C-infinity, okay? Otherwise, when you add the blue curve with the pink curve, at this point, you will, if this thing is not C-infinity here, then this thing will not be C-infinity. And now, it's very easy to convince yourself that the necessary and sufficient conditions that for these odd extensions to be smooth is that the even order derivatives are 0, okay? So the interpretation of those constraints that appear in this very simple model is actually quite nice. It's actually a consistency requirement for the dynamics that it is not that obvious when you look at the problem. But in this setting appears, of course, again, this is known. I mean, mathematicians know this. But in this setting, it really is given to you by the algorithm that you're following, okay? So that's one of the strong points of this method. So you move ahead, you get the solution, and you always see that this is what happens. So let me conclude here. So as I have said, the steps of the Dirac algorithm can be interpreted in geometric terms. Now, of course, when you do quantum gravity and you take the canonical point of view, the formulations that we have, both ADM and Ashtekar formulations, are perfectly okay. So this is not needed for that, okay? But we all look at other problems where we include extra ingredients, maybe boundaries, maybe we modify the dynamics. And in those settings where you don't know what you want, what you're going to find in the end, it is really very important to have a procedure that you can follow and without making mistakes to get the right results. So my message is, if you can use the Dirac method, it's perfectly well, but if you are working in a situation which is not familiar, for example, when boundaries are present, this geometric perspective is really very helpful to avoid making mistakes, okay? From a conceptual point of view, the main idea is a very simple but powerful one, which is this idea of tangency of the Hamiltonian vector fields to the constrained hypersurface. As I said, from the practical point of view, the computations are very easy to follow because you don't have to use complicated formulas to compute Poisson brackets, but basically you have to do what I showed. Just match terms in some expressions. Again, a warning, you really need to be careful with, if you really want to do things right, you have to be careful with functional analytic issues, and that is complicated, okay? Can be done, but it is complicated. And as I mentioned also, there is a similar approach, which is this GNH method. This is inspired actually in this method, that is slightly different, but it may be useful if you are not worried, for example, about quantization, but only about the classical mechanics. The classical dynamics of the system. And I will finish here. Happy birthday, Jurek, and thank you for everything.
Okay, so our time for questions.
Yeah.
Standard first-class system formulated in this language and using this way of the tangency condition in order to apply the algorithm. Now, let's say we have the first class system, we have found all constraints, we have the arbitrary UN Lagrange multipliers, and I would like to add a set of gauge fixing conditions. I guess you can still analyze their stability using the tangency condition, but usually we require more also that the Poisson bracket between the set of gauge fixing conditions and the original constraints is somehow invertible in order to construct the Dirac bracket. So how could is there something similar in that language?
Okay, so when you have a gauge symmetry, what happens, and it happens in this example, is that there are some components of your Hamiltonian vector field which are not fixed. They are not fixed on the final constraint submanifold that you have. Now, if you impose, if you want to enforce some gauge fixing condition, actually what you want is that your Hamiltonian vector field is tangent to the submanifold of the constraint submanifold that is defined by this extra gauge fixing condition. So what happens in practice is that you compute this tangency condition over the gauge fixing, and that will fix at least some of the components, the arbitrary components of the Hamiltonian vector field. And that's it. So so you can actually rephrase what the gauge fixing means in these terms. And again, it just boils down to a tangency, an additional tangency condition that really fixes some or all of the components of the Hamiltonian vector field. Yes.
Other question?
Maybe a bit of a naive question, but if I understood correctly, initially you were studying the stabilities of these secondary constraints, and you showed the difficulties that they were in applying the Dirac algorithm, so you didn't know whether they were tertiary constraints or they were automatic. Yes. Now, at the end of the day, with this alternative construction, is there something analogous to the distinction between the presence of tertiary constraints or not, or you don't wonder anymore about tertiary constraints?
No, you will find extra constraints as these tangency conditions. So when you do the computation, okay, in those examples where you can really follow the Dirac algorithm without any abstractions, then you can really match, there is a perfect match between the constraints that you find by using just the standard Dirac method with Poisson brackets and the things that you find here. Actually, they appear in the same order. So you can interpret the constraints that appear here as tertiary constraints. Actually, this procedure is better in the sense that somehow if you just follow formally the Dirac approach when boundaries are present, then at some point you get stuck because you don't know how to continue, whereas here you can't really go ahead.
But then would be the interpretation that there is infinitely many tertiary constraints, or rather that you have tertiary quartic, because at the end of the day you find an infinite tower. So the analogy would be
secondary constraints.
Sorry?
So, I always call these things secondary constraints, but they appear in stages, so there will be
so it would be like
you
would have an infinite
the same as in the Dirac method. This is not different from the Dirac approach. It's just a geometrical interpretation, but it's really the same thing.
So if Professor Kijowski were here, I think I don't see him today. He would say that Poisson bracket and Dirac bracket were introduced when people didn't understand the geometry of this symplectic space and quotienting by constraints. That we should rather use symplectic form because it has nicer nicer properties with respect to pull back to the constraint surface. Of course, it doesn't solve the problem because this symplectic form it is written in terms of in our case in terms of integral with some measure, and obviously we usually end up integrating in such cases some functions which are not really functions, which are some distributions, and then this is a and then it's also very likely they are not, some expressions are not well defined.
Okay, let me say something about that. This has to do with these functional analytic things that I skipped during the talk. Now, you really need to be, when you want to make actual computations of Poisson brackets, you really need to specify what your functional space is. So suppose that you are in a very simple situation where your configuration space is modeled as a Hilbert manifold on a Sobolev space. So you have a Sobolev space, you have a scalar product that involves not only the values of the function, but also the values of the derivatives. In those situations, some things that appear to be very pathological may actually be continuous linear functionals and differentiable and everything. So when you write the canonical Poisson bracket, you actually have to write it in terms of this Sobolev scalar product And if you do that, these objects that seem to be distributional or more complicated are actually have very, very nice expressions, and you can actually do the computations. I can give you concrete examples if you want. But that is a central point in this business. And that is also complicated because once you introduce functional analysis, things are not, they are complicated. If you look at the original G&H paper, where they are very careful with these functional analytic issues, you have to worry, for example, about tangency. In most cases, you cannot just require strict tangency, but only tangency to the closure of something. And then that's much, much, much harder to handle. There may be ways out of that, but we can discuss that in private. That's a long discussion, okay? Yeah, but that's a very important point.
Okay, so let me just ask a quick question about, as you said that these functional analytical issues are important and so on. And at one stage you sort of made your phase space to be the first Sobolev space H1 because it was, your phi was in...
That's one example, but of course...
Okay. But of course, that's not viable, right? Because at the end, you have these conditions which require infinitely many derivatives.
Sure. I'm not doing this here. I didn't want to mention that here. I was just saying that if you're working in the cotangent bundle of such a space, then you would not have any problem. But here you must be very careful with that, because if you just work in the first Sobolev space, then of course after one step...
So in this case, what is your phase space? I think it would have to be some Frechet manifold because you need infinitely many conditions. So.
Okay, there are several ways out. If you relax the tangency condition to this tangency to the closure that Gauthier, Nestor, and Hinz use, then that is enough to make things consistent. You can start, for example, with a Sobolev space of fixed order, and then the algorithm would stop precisely when you run out of derivatives. Okay. So that works, and that is actually...
You can go to, it's not, you don't need a finite number. You can
yes, you only get a finite number of these
But here you
constraints.
get infinite power.
Yeah, so this is formal in the sense that as I said at the beginning, I'm pretending that I have a smooth things and I can go on with the algorithm. Of course, if I want to work in that space, that's complicated because C infinity with the standard semi-norm is a Frechet space. And you can maybe fix that if you find some Sobolev space, which is smaller than the space of C infinity functions and is stable. But that is, you have to figure out how to do that. I think it's doable, but I have to work a little bit more on that. But yes, you're absolutely right.
Okay, so we stop now for about 25 minutes for the tea break, or 24 minutes, or 28 minutes for the tea break, and we come back at 10:50. Right? 10 minutes to 11. Okay, let's thank Fernando again.
Thank you.